We've now seen how homeostasis is regulated and maintained in the cell and the body. But can we take it a step further and observe homeostasis in other complex systems? For instance, an ecosystem. Before we do this, let's review what homeostasis is. Homeostasis is the tendency to maintain and restore steady state conditions required for life. So the key concepts of homeostasis are an observable steady state that defines our normal. Thresholds that fall above and below this normal range that are also acceptable within homeostatic conditions. Third would be the ability to sense changes to the steady state, which I'm going to abbreviate SS from this point forward. So steady state is SS. And lastly, the ability to restore steady state. So what actually causes a deviation from steady state? Or in other words, what is driving homeostasis? And the most broad but straightforward answer is actually changes in energy. So systems have defined energetic states for which life is sustained. For example, humans have optimal blood glucose levels, body temperature, blood pH, and these are all tightly regulated. And it may seem abstract at first to think of these notions as energy. But if we recall two concepts, that energy is the ability to elicit change to matter. And the second, that there are many forms of energy. There's kinetic, potential, chemical, thermal, and electrical, among others. So it's easy to connect how, say, changes to blood glucose levels in the body is actually a change to energy in the body. And when we think of homeostatic regulation and factors that influence homeostasis, we can take a step back and keep in mind that the driving force of homeostasis is changes in energy. So when a deviation goes beyond either the upper or the lower threshold, energy is mobilized to restore the steady state to its optimal value. Always recall, though, that because of these thresholds and the nature of feedback systems, the system oscillates around the steady state, and that the steady state is restored through a series of feedbacks that draw the system closer to its normal. So if we look at this graph here, and we have our normal blood glucose level, so our defined normal level, and say we eat a big juicy hamburger, our blood glucose levels are going to spike. And the body is then going to enact a series of negative feedbacks which will draw the system closer to its optimal level. But in doing so, we actually overshoot and overcorrect from the optimal level. So you can see that in fact we oscillate around the steady state, and that the oscillation actually dampens through the feedback. So if we think about our black box model, we still have our inputs, our outputs, and the black box itself. Just as before, we can expand the definition of the black box to now actually encompass an ecosystem.